Hello and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 43, which is gate all around FET, and we will be looking into the device design perspectives. We will be actually working on GAA structure, which is gate all around, and these are basically sort of sub 5 nanometer devices. We will look into nanosheet FETs and then look into process variation, and then maybe give you an analog perspective of nanosheet FETs in terms of how these nanosheet FETs or gate all around devices can be used for analog processing. So, the first outline for this lecture will be to give you an idea about the roadmap for short channel for FETs, and that is basically using a high K material. What is the meaning of high K dielectric material? A brief history so that you can appreciate how GAA FET were formed, various gate all around structures, and then finding the folding ratio of GAA with respect to FinFET. Now, typically when you look at dielectric, the scaling of silicon dioxide, you do a scaling of silicon dioxide, right? Because when you are scaling a device, the oxide thickness also scales down, because you want the electric fields in transverse direction to be also scaled down. So, what you do is that you scale down your gate voltage, but then you need to scale down your T oxide, so the electric field remains almost constant, and that is the reason you require to have these oxide materials being made shorter and shorter. And this is an effective approach in all your CMOS technology. For all your CMOS technology, reducing the value of Tox is a very effective way of improving the characteristics of the device. Now, in the past quite a few decades, we have seen the reduction in the thickness of the silicon dielectric, silicon dioxide dielectric, has enabled a large increase in the number of transistors per unit area, right? Which means that the device density has actually increased. The device density has actually increased because of this. However, as the device approaches for the 45 nanometer technology node, around 45 nanometer technology node, the effective oxide thickness of traditional silicon devices should be actually very small than 1 nanometer. Right. So, it will be smaller than 1 nanometer, which is approximately sort of 3 monolayers of atoms, and therefore, what is happening is that there is a physical limit to which the oxide thickness can be grown. There is a physical limit to the oxide thickness, right? There is a physical limit there, which tends the oxide thickness to grow. But what happens is that to continue downward scaling, you actually require a high K dielectric, which means that I can lower the value of Tox, but I ensure that it does not break down. And so, what you do is that you replace the conventional silicon dioxide by a high K material. High K material, basically HFO2 being one of the primary solutions for that. So, there are many candidates which are there. One of these hafnium based oxides. There are a large number of hafnium based oxides available. Then there are zirconium based oxides or materials and oxides, right, which also acts as an insulator between them without degrading the interface. So, that is also pretty important from a designer point of view, that when you grow an oxide layer, you need to ensure that the material which is being used to grow the oxide layer on the top of the silicon layer does not change the structure of the silicon itself over which it is growth is taking place. Now, these are one of the basic sort of input elements which you can give in the place of oxide. Now, one key issue which raises, so this is the 1, 2, and this is the third issue, is basically concerning the new dielectric material, either hafnium based or zirconium based, is that most of the material actually gives you a comprehensive enhancement in the performance, but has a low crystalline temperature. has a low crystalline temperature, right, low crystalline temperature which is formed, and therefore it is very difficult to integrate with the conventional CMOS process. Therefore, it is difficult to integrate with the conventional CMOS process, and that is the major problem area which you face when you actually want to inculcate oxide layers within the conventional CMOS process. Now, what are the basic requirements of high-K dielectric? First is obviously should be a good insulating property. It should have good insulating property, and the second important point is that its capacitance performance. Both should not be performance. So, both should not be compromised. So, one is a good insulating property, another is a capacitive performance. Now, the problem is as you go on doing the scaling, if you lower down the dielectric thickness, there might be a finite probability of direct tunneling which might happen through the oxide layer. So, having a good insulating property is important, and the second part is the capacitive performance, primarily meaning that its capacitive degradation should not take place because of a bad interface between the silicon dioxide interface. Basically, what you need to do is that you need to prevent defects. Why we need to prevent defects? Because we do not want trap formation to take place within the oxide layer. That will degrade the overall characteristics there, and we want to have as fewer number of electrical defects as possible, which will ensure that that the design is much more reliable, or the device design is much more reliable in a sense. It should also have good thermal stability. It should have a good thermal stability, right, and high crystalline temperature, and obviously a better reduced or a better quality of interface. Now, if you therefore plot basically gate oxide thickness versus years, then typically what happens is that it is, let us suppose this is 1990 and this is about 2005. I am giving you a slightly old data. It is basically falls down drastically. It falls down to a very low value. So, typically in 2005 this is around 1.5 nanometers, whereas around 1990 this was around 9.5 to 10 nanometers approximately, the gate oxide thickness. So, this is in sort of log scale which you are seeing. This is 10 and this is very near to 1. And this is the major sort of challenge which people face while designing this oxide thickness. So, let us come to this thing, the technology roadmap for short channel FETs, and as I discussed with you currently that with the continuous gate length scaling, we require a new modification in the device and which can improve the device performance. So, the idea here is that if you do not reduce your oxide thicknesses, you end up having strong electric fields available, and they might destroy the performance of the device. And secondly is that if you go very small in oxide thickness, there might be a problem of direct tunneling through the oxide layer. The problem end up is that you have a large leakage current. As I discussed with you earlier, there are alternative dielectrics available with us. If you look at the diagram which is mentioned below, this is a sort of a roadmap which we see, that when we were working with 90 nanometer technology node, we used in the materials silicon, germanium, strained silicon. Then at 65 nanometer, second generation silicon, germanium and strained silicon. 45 to 22 is where we introduced high-K dielectric. Then we enter into tri-gate FinFET, and then 3-5 FinFETs, and then future GAA device. So, what we will be concentrating is basically the future GAA device here. These are the future GAA devices. We will be having a look at these devices henceforth. As I discussed with you, the multi-gate device can now be expanded beyond the bulk CMOS with high-K material. Now, when I say high-K material, please keep in mind that its dielectric constant is relatively high. One way of doing it is that keep a high K dielectric material in the channel length of the device, and this will improve the efficiency of the device as well as the reduction in the short channel effects. Now, uh, if you look at the capacitance performance, let us look at the cap performance. Then if you look at the cap performance, typically K should be over 12. So, it should be greater than 12, and the typical value of K is between 25 to 30. And therefore, an appropriate K value means that the dielectric will have large physical thickness, which will prevent the gate leakage, and therefore I of will be reduced, and also not too thick to hamper physical scaling. So, that is where the challenge is, at least for the dielectric, that it should not be thin enough to induce tunneling, and it should not be thick enough to sort of be an impediment in scaling the device. Now, typically what happens is that if you take a very large K dielectric, you then end up having a large fringing field, and which adds to the capacitance value. So, these parasitic capacitances tends to reduce or degrade the dynamic performance or transient performance of the device. So, you need to play with all these factors in order to ensure that the device is in the proper state. Now, let us look at the left hand side graph here, the possible dielectric material and the constants. So, one is look at the outlier first. So, let us look at the two outliers which we see here. The first outlier is silicon dioxide, which is around 3.5 to 4, and the other one is titanium oxide around 60, right. 60 is very large, but the problem is that these titanium oxides, which are very large, do have a band gap which is about 3 electron volt, right, and that is the cost you pay for having a higher dielectric constant. Every other material, silicon nitride, titanium oxide, yttrium oxide, calcium oxide, zirconium oxide, hafnium oxide, lanthanum oxide, barium oxide, they all fall on that narrow sort of hyperbolic curve which you see, right. And if you look carefully, the values, so as you make your K value higher and higher, you see the cost you pay is that a band gap starts to reduce, and therefore direct tunneling probability increases. Now, the schematic of direct tunneling through silicon dioxide can be seen in this figure here. So, I have this silicon dioxide and I have this high K oxide being inserted into it, and through the gate there is a direct tunneling of the electron, and it goes from a region of high concentration to a region of low concentration. As a result, there is a I of or off current becomes relatively larger, right, and that is the reason we have a direct tunneling through the silicon dioxide. Now, one of the most popular elements for high K material is hafnium oxide, and because it has got a relatively high dielectric constant, right, and also a large band gap, and it is also thermodynamically stable on silicon. So, these three properties of silicon, of hafnium oxide, actually makes the material a very popular material in terms of its usage for silicon dioxide. Now, so typically the band gap which we use is 5.68 electron volts, and it helps you to give a lower power consumption. Now, moreover, the crystalline HFO2 has a much more lower leakage current, and many of the binary oxides, because of the relatively high value, have been adopted. So, if you look at the figure here, which is basically a TEM image, these are basically this is crystalline HFO2 and silicon dioxide. In the first case, it is 40% HFO2, in the second it is 80% HFO2, right. So, this is a TEM image or TEM image of the crystallization in hafnium oxide silicon dioxide dielectric. So, it is a mixture of two type of material, hafnium oxide and silicon dioxide, and they are using 40% HFO2 and also 80% HFO2. Now, An important property which you should be like aware of, and that is very important, is known as EOT, or equivalent oxide thickness. Now, an equivalent oxide thickness basically is the distance given in nanometers which indicate how thick a silicon oxide film would needed to be produced so as to have the same effect as the high K material being used, right. Which basically means that if I have a silicon dioxide material, right, and I replace that by say hafnium oxide, then we define the effective oxide thickness, or EOT, as the minimum distance of the hafnium oxide which will result in the same output characteristics as that of the silicon dioxide, right. And EOT is given by this formula here, that it is T high dielectric. T high means the thickness of the high K dielectric, and K silicon dioxide upon K high K dielectric. So, it is basically T high K, and this is silicon dioxide K value upon K high K. This is your effective oxide thickness. See, if you keep everything same, as you tend to increase the value of KHK, higher value, for the same EOT you also need to raise the value of THK, right. So, that is what I wanted to say, that if you want to discuss about effective oxide thickness higher value, then for a higher value of KHK you will require a larger value of THK in order to form the same amount of output characteristics, and is given by EOT here. For example, let me give an example, say K silicon dioxide is known to me and K high K dielectric is also known, but so this is 3.9, let us suppose, and this is 40, and if high K material is say 10, then it is 39 by 40 happens to be EOT here, right. If now if I increase this material by 50, make it 50, then what I get is I get 3.9 by 5, and that has a point approximately 0.8, right, and this would have been approximately some value here. Now, you see the change EOT changes just because by changing the thickness of the high K material, right. Okay. What are the challenges of scaling and what are its possible solution? The challenges in scaling are multiple. For example, when you work with less than 0.1 micron technology node, for example in bulk MOSFETs, right, the main issues are low drive current and short channel effects. Why? Because when your channel lengths are relatively high, for any FET device drain current is proportional to W by L, right, drain current is proportional to W by L. So, when you start to make your length larger and larger, your driving capability starts to reduce, right, and as a result what happens is that your ID drain current starts to fall down. The possible solution has been used by quite a long time and for a large number of device technologies. We use strained silicon germanium. When you use a strained silicon germanium, you end up having a larger mobility because strained silicon gives you a larger mobility of the charge carriers. Then if you are working at 0.1 micron to 32 nanometer, right, then basically we talk about the best device which people have proposed over a period of time is the silicon on insulator MOSFET or soy MOSFET. However, it has issues with leakage current and excessively large power, right. But the solution to that is to have an ultra thin body or UTB SOI in this case. That will actually reduce a large amount of leakage current. Then when you go to 32 to 10 nanometer range, which is quite low, the channel dimensions are very low, then the device performance which comes out to be very good is basically your FinFET. And short channel effects are prominent, obviously because you have reduced the channel dimensions to small value, but the solution for them is to have a multi-gate material, which means that can we have a multi-gate material available with us, right. So, all the sides of the gate are surrounded by the same material. You can also have multi-channel. Multi-channel means rather than having a single channel between source and drain, can we have multiple channels, because to offset for a lower current, can I have a larger number of channels available to us. And another one which is there is basically the stack oxide. Stack oxide means there are two ways of stacking an oxide layer. So one is that if you place silicon dioxide, so this is silicon, let us suppose this is silicon dioxide. You don't want to make the interface bad. So what you do, you grow silicon dioxide over silicon, and then you grow hafnium oxide over that. This is known as stacking of oxide layer, right? And you can do stacking by just doing an epitaxial growth or even a simple oxidation which can happen over silicon dioxide. Uh, Less than 5 nanometer, which is where we are talking about this lecture, we use gate all around devices, GAA devices. Obviously the issue is area and cost. Obviously the current is very large, therefore power is an issue. However, many solutions are available on board, and these are multi-bridge solutions and have multi-bridge channel solutions, such that you have multiple channels within the device which will be having the current high, but then the current density will go down. There will be no hotspots for power available within the active area of the device. So these are the few scaling challenges and the possible solutions as per our understanding. Now if you look at GAA transistor or gate all around field effect transistor, now in this case the gate material will actually surround the channel from all the directions, and this will lead to an unprecedented electrostatic control. And so the rule of thumb is, better you are able to control the channel by the gate, lower will be the short channel effects, and therefore GAA FETs have very low short channel effects as such. Now GAA FET devices were initial phases around 1988, right? However, first time Fujio Matsuoka from Toshiba Corporation and his team made a demonstration of a vertical nanowire GAA FET, and they termed it as surrounding gate structure. So what happens in surrounding gate is, if this is the channel, you are surrounding it from all the 4 directions, like the palm of my hand surrounding this device, right? And the channel is actually moving in this direction. The channel is in this direction. The current is moving in this direction, and the channel is formed in the circular direction. Now this gives you obviously a much superior electrostatic control. So your short channel effect goes down drastically, and you are able to maintain a high value of reliability of the device. Now as I discussed with you, therefore the gate contacts are in the channel, are from all the sides, and major foundries have done quite a large amount of work around 3 nanometer and 2 nanometer nodes by reducing the FinFET device, scaling the FinFET device, and looking into the issues. The sort of pediment blocks are channel width variation and so on and so forth. Now what advantage of this is that you will be minimizing the short channel effects drastically, even as the device dimensions are shrinking down, right? So if you are able to sort of control of the channel using a bias from all the directions, it will be much better in terms of minimizing the short channel effects. Let me come to the various types of GAA devices. We have a triangular GAA device, we have a nanowire GAA device, and we have a nanosheet GAA device, right? And out of which many of them came from industry, but surely multi-bridge channel MCB came from Samsung initially. The nanosheet FET came from IMEC Belgium, and nanoribbon FET came from Intel, right? And these were the companies who gave the device first time the device outlook or the device dimensions. These are the types of devices. The triangular GAA device which I want to show and give you an idea about it, and looking into the E density plot here and electric field density plot. So since it is an electric field, what you can see here is that near the edge the electron density is relatively high, right, and expected also because the electric field tend to become very large. However, if you reduce the dimension drastically, you see suddenly the electron density becomes large at the center of the triangular fin device, right, and this is known as quantum confinement which happens. So what you see is the first 2 graph is electron density, and the last graph which you see is basically the absolute value of the electric field which we are proposing, right. And as you can see, it is maximum at these edges with the electric fields are very strong. Why? Because you have got now typically two component of electric field available. One is horizontal going inside the material, and another longitudinal which connects source to drain, because of which the electric fields here can be written as Ex square plus Ey square root over, right. And this gives you a brief idea that triangular, though it is easier said than done from simulation point of view, its fabrication is rather more difficult, right. So, we will stop here today, and what we learned from all these discussion is that we require a high K material. We also require that the channel should be surrounded from all the directions for reducing the short channel effects, for example dibble, for example gate leakage current, for example direct tunneling current, and so on and so forth. Further, if you reduce the oxide thickness to a very low value, the direct tunneling current precedes over anything else, because of which the off-state current actually increases, right. So, when we meet in the next turn, we will discuss about the further areas of the GAA devices. Thank you.